Good evening and back to this problem session for the engineering. So today we are in grade 6 and we'll start this session with one homework problem which we took in the last class. Okay, so we'll quickly see. So this is the homework problem which was given in the last session, and it's about the determination of the length of a combined trapezoidal footing. So a combined trapezoidal footing of length L supports two identical square columns. So these columns are marked as P1 and P2 in this figure of size 0.5 meter by 0.5 meter as shown in the figure given below. The columns P1 and P2 carry loads of 2000 kN and 1500 kN respectively. Now, if the stress beneath the footing is uniform, the length of the combined footing N is okay. So, as we can see from this problem, that here both the sides of the footing, that is left hand side and the right hand side, dimension are given as 5 meter and 1.5 meter respectively, and the columns which are basically supported by this footing, the dimension of these columns are also given as 0.5 meter by 0.5 meter along with the center to center distance between these footings as 5 meter as given in this problem. So in addition to that, the load which is basically carried by these columns, the magnitude of those loads are also given to this problem as 2000 kN and 1500 kN respectively. Now what we have to determine? So we have to basically determine the length of the footing in such a way that the distribution, stress distribution beneath the footing should be or must be uniform. Now how we can ensure that the stresses which is basically caused by this kind of loading, which is basically coming from the superstructure, here superstructure in the sense these columns, must be uniform. So how we can ensure? So we can ensure obviously by designing this L, but what should be the criteria before determining this L? And by imposing which condition we can determine or we can approach to determine this dimension L. Okay, again for your kind information, this question basically taken from GATE examination 2021. Okay, so therefore this type of question is very essential to at least the approach how you can basically solve this kind of problem matters for basically scoring a good marks in this type of competitive exam. Okay, any idea? Okay, so the fundamental to this problem is all about the distribution of stress beneath the footing. Okay, so suppose I am drawing the elevation view. So this is the base level of the foundation, and we are trying to assure a uniform distribution of stress beneath the base of this footing. So this is sigma. Okay, the intensity of stress beneath the base of the foundation we are denoting as sigma. Now this sigma can be due to two components. First of all, axial stress, and the second component is due to moment. Okay, so axial stress divided by the area, that will give you stress, one component of stress beneath this foundation. This is purely compressive stress, obviously compressive and axial compressive stress, and this component is nothing but the stress which is basically caused by the bending moment or moment, okay, which is basically applied, externally applied to this foundation. Now the question is, we can easily understand that this footing is basically subjected to two axial loads of magnitude 2000 kilonewton and 1500 kilonewton. Now, is there any moment apart from these two loads? Is there any chance to build up any moment on this foundation apart from these two loads? Because this footing is combined. Or I can ask, on what or in what scenario there is a chance to build up of any external moment on this footing. Now please remember that to get a uniform distribution of stress beneath the foundation, we have to have just only the first component, that is P by A. P is the axial load which is exerted on the footing, and A is the footing area, the cross-sectional area of the footing. So if you divide the load, the total load which is supported by the footing by the area, cross-sectional area of the footing, then the stress which you will be getting, that will be uniformly distributed beneath the or along the base of the footing. Now if you consider any stress due to applied moment, so as soon as you will be considering any stress due to the applied moment, so you will be getting something like this type of distribution. Okay, so sigma max on one end and sigma mean on another end. Now sigma max will be due to positive sign, so P by A plus My by I, and sigma mean will be due to minus, so P by A minus My by I. Here M is the moment, Y is the distance from the center, and I is the moment of inertia of the section. So when the moment is basically applied in this direction. Okay, so if it's applied in this direction, the sense of moment, applying moment, is very, very essential. So in that case, the distribution will be reversed. So here it will be sigma mean, here it will be sigma max. Okay, so therefore it's obvious that we should try that there should not be any buildup of externally applied moment. Now how we can ensure that there should not be any moment on this footing? So this component, if you consider this component, then only you will be getting a non-uniform distribution of stress beneath the foundation. Otherwise it's fine, it's okay. So you will be having only the first component, and that will be uniform. So it is only possible, so suppose this is the plan area. So right now I am giving you the example of a rectangular. Okay, now as you know that the CG of this footing will be at the center of this rectangle. Okay, means if this dimension is B or L and this dimension is B, so if we consider along the length direction, then it will be at a distance of L by 2, and if we consider along the width direction, it will be at a distance B by 2 from any side of the footing. And the load which is supported, so it can support multiple number of loads. Suppose it's supporting P1, P2, P3. Okay, it's a kind of wrap foundation. Okay, so it's supporting multiple columns, and multiple columns are exerting multiple number of axial loads. Now to ensure the condition of no external movement on this footing, you have to must ensure that the resultant of these loads should pass through the center of this footing, the centroid, center of gravity of this footing. So this is the condition to get no externally applied movement due to the application of external loads which is supported or which are supported by this footing. That means the resultant of all these loads the series of loads should pass through the CG of this footing, CG of this cross section of this footing. Okay, so the similar phenomena or similar strategy you can also apply in this case as well. Okay, so now first we have to determine how to determine the location of the resultant of these two loads. So right now we are dealing with two axial loads, P1 and P2, which are passing through columns P1 and P2. So therefore, in this problem, we have to basically determine the location of this resultant of these two loads P1 and P2. So how we can determine the resultant of these two loads? So this is, if we basically draw a line diagram, so this is your P1 and this is your P2. Now, you know this distance as 5 meters and this distance 0.5 by 2, that is 0.25, or we can write here 0.5, because the cross section or the dimension of the footing is, both the footing is 0.5 by 0.5 meter. So this dimension is your 0.5 meter and this dimension is your 0.5 meter. That is, it's a square column. So obviously you can take the reference point, so about which you are trying to determine the location of the resultant. So you can take this as the reference point. So this point, this left hand side. Okay. Now from this left hand side, you can easily determine the resultant. Suppose the resultant is basically located at a distance of x bar. Now how we can determine this x bar? So x bar we can determine by taking the moment. So basically equating the moment about this point of this individual loads. We can first determine the moment of this the moments caused by these two loads about this point, and then we can easily determine the moment caused by this resultant, and then we can easily equate these two moments and we can determine the location of this resultant as x bar. So therefore ultimately we'll get this kind of expression. So pi xi, so this is the moment this is the summation of moments of these two loads P1 and P2 about this point, and this is the moment due to the resultant, okay, R multiplied by x bar. Now what about pi and xi? So this x bar, so P1 x1 P2 x2 divided by R. Now P1 we know it's 2000 kilonewton, then P2 we know it's 1500 kilonewton. Now what's about this x1 and x2? What are the values for this x1 and x2? What would be the value for x1 and x2? So this distance is your x1. Since you are taking the reference at this left hand side, okay, and this is your x2. That means the lever arm of P2 and P1. Now what is the value for x1? It's simply 0.25 meter. And what is the value for x2? It's simply 5 plus 0.25, that means 5.25. Okay, So this value is 5.25 meter and this value is 0.25 meter. Okay, so this is 0.25 meter and this is 5.25. Now it becomes very easy to calculate x bar. So 2000 multiplied by 0.25 plus 1500 multiplied by 5.25 divided by the resultant. Resultant means P1 plus P2. So 2000 plus. Now what would be the answer? Can you please let me know what would be the answer?
2.39.
2.39. Very good. Okay. So that means this x bar is 2.39 meter. Now, to get a uniform distribution of stress beneath this footing, we must keep in mind that the CG should be exactly at a distance of 2.39 meter from the left hand side of this trapezoidal cross section. Now, how we can determine the CG of a trapezoidal cross section? If we know the dimensions of the footing, means the trapezoidal cross section, that means the left side and right side and as well as the length. Right now you basically take the or consider the length as L. Now what is the formula for getting the CG of a trapezoidal cross section? So instead of trapezoidal, if it is rectangular, then it would be simply what? It will be simply what? L by 2, na? But this is not the case. Okay, so CG of a trapezoidal cross section. So I am giving you the formula, though you can basically derive this equation from the very fundamental. So if this is the trapezoidal section with a length L and the sides as A and B, so the CG from the left side with this dimension x bar, it will be L by 3 A plus 2B divided by A plus. Okay, so please keep in mind that the reference line we are taking at the left edge of the footing. The left edge or left side of the footing, we are taking the reference line. Okay, so if you reverse it, means if you take the right hand side as the reference line, then this equation will be slightly different. So in that case, it will be B plus 2A by A plus B. Numerator will be only changed. Okay, the numerator or the denominator will not change. Okay, now in this case, this A value is given as 5 meter and the B value is given as 1.5 meter. Then what will be the value for x bar in terms of L by 3? So 5 plus 2 into 1.5 divided by 5 plus 1.5. So what would be the value? 8 divided by 6.5 divided by 3. 16 by 39 L or 0.41 L. Okay, 0. Now for a uniform stress distribution, beneath the footing, these two values should be equal. This 0.41 L and this 2.39 meter. Okay, the resultant of the applied loads is basically passing through the CG of the cross section. If it doesn't, then there will be a externally applied movement, and the distribution of stress beneath the footing will no more be uniform. Okay, so therefore this 0.41 L should be equated to 2.39 meter. So please work out what would be the value for L.
5.829.
5.83 meter, na?
Yes.
Okay, very good. So this is the this much length you should provide to get a uniformly distributed stress distribution beneath the footing. Okay, so it's very simple and straightforward. Just you have to keep in mind two things. So first one, how to determine the resultant of a series of loads, and secondly, you have to determine, or you have to know the CG of this trapezoidal cross section. Not trapezoidal. In exam you may encounter some another cross section, triangular, circular, square. Okay, so depending on the cross section, you should know what should be its CG. Okay, the location of center of gravity. Okay, so this was the homework problem. Okay, I think I have a question. How the distance? Okay, can you please read the question once? Can anyone please read the question? How the distance between the two loads is 5 meters set. Okay, so it's given, na? It's given in this problem. You no need to assume that this center to center distance between these two columns is 5 meters. The dimension at the sides, that is left side and right side, given. The center to center distance between these two columns is given, and the dimensions of these footings are given, and the magnitude of loads which is supported by these columns are also given. Here the only unknown is the length of the footing. Are you getting my point? This 5 meter distance is given. Okay, otherwise it will be very difficult to calculate this L. Okay, then you cannot calculate this resultant. You cannot calculate, you can calculate the CG, but you cannot calculate this resultant, location of the resultant, if you don't know the distance between these two rows. Okay, okay, so I hope I answer your question. Okay, now coming back to this week 6, the content of this week 6. So in this week we have started a new topic, that is deep foundation. Now before going to that topic, so at the very beginning of this week we solved 2 example problems. So the first example problem is about determination of factor of safety against bearing and sliding for a rectangular footing which is subjected to both eccentric and inclined loading. So earlier in this course we have solved all the problems with eccentric, not all the problems, I think 1 or 2 problems with load applied at some eccentricity from the center of the footing cross section. Now in this problem we have seen that the load is basically applied at some eccentricity along the width direction from its center of the cross section, and again the load is having an angle with the vertical direction. Okay. Now this problem we have solved based on Meyerhoff's theory, Hansen's theory, basic theory, IS code method, and lastly we draw a comparison considering all these theories. Okay, so that means this is a sort of comparative study. Now in the second problem, we have determined the net ultimate bearing capacity of a rectangular footing resting on cohesive frictional soil, cohesive soil, and cohesionless soil. And again, considering all these theories, and finally, we have drawn a conclusion regarding the net ultimate bearing capacity, means the what I can say that whether in case of cohesive frictional soil or cohesive soil or cohesionless soil, the net ultimate bearing capacity is greater as compared to the other scenario. So I think in last session or last session, some of you asked about that in which kind of soil, purely cohesive or purely cohesionless soil, this bearing capacity would be maximum or bearing capacity would be greater or higher. Okay, so through this problem I think your question is basically answered. Okay, so as you can see that for cohesionless soil we have got the higher net ultimate bearing capacity, and I hope considering all these bearing capacity theories, Feljagi's, Meyerhoff, Hansen's, basics, and IS code. Okay. Okay. Now, after solving these two problems, we have seen the stress and settlement profile beneath the foundation. Now, this profile we have seen for two scenarios, means the considering the rigidity of the footing or foundation and considering the type of soil. So, as a whole, we have seen four profiles for flexible footing on cohesive and cohesionless soil, and flexible and rigid footing on cohesive and cohesionless. Okay, and this is also very important aspect. So this type of question you may expect in this competitive exams like GATE, ESE, and so on. Okay. Then we have started learning this new topic called pile foundation. Now, firstly, we have seen what are the uses of piles. So these piles are basically used to carry vertical, incline, and horizontal load, and in some cases to resist uplift load. Now, these piles can be these piles can be classified into different categories based on the material used, cross section, shape, mode of load transfer, method of installation, method of forming, and the displacement of the soil. Now, the application of an individual pile, it basically depends on its suitability to some specific circumstances. So we can take an example. So the example is like that depending on the shape, we can classify the pile as cylindrical with uniform cross section, then tapered and underlaid. Okay. Now, as you have learned from this course, that this cylindrical pile is basically most beneficial for cohesive soil underlain by a granular soil deposit. However, tapered pile is basically most useful for loose to medium dense sand, and underlain pile is basically useful for expansive soil. Okay. So this type of question also you can expect in the examination. Now, in the next topic, we have seen the typical length and capacities of various piles, and lastly, we have started the computation of pile load capacity in compression considering static pile load formula. Now the static pilot formula. So under this heading, we have seen Tomlinson's method, Meyer solution, and Indian Standard 2911 Part 1 2010. And all these formulas, right now we have seen the application of all these formulas, particularly for granular soil deposit. Okay, and at the end we solved a couple of example problems. Okay, so therefore in this session we'll mostly try to solve a few problems concerning these topics: the calculation of payload capacity, obviously in compression, and for purely granular soil deposit. Okay, depending on various solutions or methodology. Okay. So first we'll take a problem regarding this aspect: a footing subjected to eccentric inclined loading. Okay, so first we'll solve this problem and then subsequently we'll move on to the pile foundation part, estimation of pile load capacity in purely granular deposit. Okay, so this problem is basically taken from Engineering Service Examination 2023, and it's mentioned like that: a 6-meter high pier rests on a 2 meter by 2 meter square footing at 1.5 meter depth from the surface at a site having uniform clay soils. The unconfined compressive strength of the clay is 100 kPa and its bulk unit weight is 20 kN per meter cube. The pier carries a vertical load of 80 kN at the center, including its self weight, and a resultant horizontal load of 15 kN also acts on one side of the pier at 1.5 meter above the surface. Now we have to determine the factor of safety with respect to the pier's net ultimate bearing capacity as per IS 6403 recommendation. So this problem can be visualized in this fashion. So the top figure, this represents the cross-sectional view, and the bottom figure represents the top view of the given problem. So this is the pier. So it's basically acted upon by a vertical load, concentric vertical load of 80 kN, including its self weight, and a resultant horizontal load of magnitude 15 kN at a distance of 1.5 meter or at a height of 1.5 meter from the ground surface. Okay, so this is the ground surface. Now this pier is basically resting on a square footing of dimension 2 meter by 2 meter, and at a depth of, this footing is basically rested at a depth of 1.5 meter below the ground surface on a uniform clay soils. Okay, now what is the unconfined compressive strength of this clay? It's basically 100 kPa. That means QU, this is given as 100 kPa. Okay. Okay. Now what we have to determine? We have to determine the factor of safety with respect to this pier's net ultimate bearing capacity as per IS 6403 recommendations. Now what we have to do first? First we have to determine the inclination of the resultant load, resultant in the sense resultant of these two loads, vertical and horizontal load, from or above the vertical direction. Okay, it's very essential to know the inclination angle, because it will be used in the calculation of the bearing capacity factors, not bearing capacity factors, sorry, in the for the calculation of inclination factors. Okay, since as you can see from this problem that there is a vertical load as well as there is a horizontal load, therefore you can easily calculate the resultant of these two, and the resultant of these two obviously will not be vertical or will not be horizontal. So it will be having some inclination from the vertical axis of the pier, okay, or the footing. So this is the angle. So this is the angle of this resultant load R, and this angle is defined by alpha. Now how we can determine this alpha? What should be the value for this alpha? So this alpha, please correct me if I'm wrong, you can calculate in this way, tan inverse H by V. Yes or no? Am I correct? This alpha you can calculate as tan inverse H by V. I think I am correct. Okay. So that means tan inverse 15 divided by 8. So it will be, I think, 10.62 degrees. So this is the vertical inclination of the applied resultant load. Resultant load of the vertical load of magnitude 80 kilonewton and horizontal load of magnitude 50 kilonewton. Now, please see that this resultant, what is the line of action of this resultant? The line of action, okay, it's having a inclination of 10.62 degree from the vertical axis. Now, what is the location of this line of action from the CG or center of the cross section? Can you please identify? Where this line of action of this resultant cuts the base of the footing. What I am trying to say, if you extend the line of action of this R, so obviously it will cut at some point along the base of the footing. So in this way. So this is the line of action. I have shown here as dashed line. Okay. So if this is the line of action of this R, so it's basically cutting the base of the footing at a distance of Ex from the center of the footing. And this is the eccentricity. So this is V, this is H, and this is the resultant. Okay, and this is alpha. So obviously this angle will be alpha. So therefore, as you can see from this problem or from this picture, that the load is having both inclination above the vertical axis as well as some eccentricity above the center of the footing. Okay. Okay. Now, how to calculate this eccentricity from the center of the footing? How we can calculate this Ex value? How we can calculate? So we can calculate from simple geometry. So this angle is alpha. This angle is alpha. This total height. So this is basically a triangle. It forms a triangle. So this. Let me use a different color. Okay, so this is a triangle, and this triangle is having a height of 1.5 plus 1.5, that means 3 meter height. So we need to calculate its base, the value of its base, okay, Ex, and we know this angle. So obviously this tan alpha would be Ex divided by 1.5 plus 1.5, that means Ex divided by 2. Okay, so from this equation we can easily calculate this Ex value as 3 times tan alpha, that means 3 times tan 10.62 degree, 0.56 meter. Now earlier we have learned, if the load acts as at some eccentricity from the center of the footing, so we know we have to use the concept of useful width. So the total width will not be effective in the bearing capacity calculation or to bear the load, because the fundamental is like that. Here the load is basically acting at some eccentricity from the center of the footing, So we'll try to remodify the cross section at this plan area in such a way that this load becomes concentric about the new plan area. Are you getting my point? The concept of useful width is based on these fundamentals that you have to remodify the original plan area in such a way that the initial eccentric load becomes concentric about the modified area or with respect to the modified area. So this is the concept behind useful width. Okay, so this would be the useful width or dimension of the useful width. This is the dimension B prime. This is B prime, and you know how to calculate this B prime value. So B prime would be the original width minus 2 times the eccentricity in that direction. So it's all about the eccentricity in one direction. So if eccentricity prevails in both the directions, means along the breadth and along the length, both the directions, then you have to modify the length as well. So L minus 2 times Uy if the eccentricity along the length direction is Uy. Okay. So for this problem, it's a one-way eccentricity. So we have to only modify the width as B prime, and which we can calculate from this equation, B minus 2 times dx. Okay. So therefore, this modified B will be 2 is the original width minus 2 times 0.56. I hope this value would be 0.88 meter. Okay. Now, this modified width you need to consider for the calculation of all the shape factors, depth factors, as basically mentioned in this table. Okay. So we have to be very careful about the calculation of these factors, because we are considering the IS 6403 recommendations, and the soil is uniform clay soils with a unconfined compressive strength of 100 kPa. Therefore, the phi value of this soil is 0. And what is the undrained cohesion value? Undrained cohesion value, it will be half times the unconfined compressive strength of the clay. That means 100 by 2, 50. Now you should know the bearing capacity factors corresponding to a phi value of 0 degree. So as per IS 6403, this bearing capacity factors are NC would be 5.14, NQ 1, and N gamma 0. And what is the bearing capacity equation? The net ultimate bearing capacity. So IS 6403 directly gives the net ultimate bearing capacity. So it will be CNC SC DC IC plus NQ minus 1 SQ DQ IQ plus 0.5 gamma B N gamma S gamma D gamma I gamma, and the water table correction factor. Now in this problem, nowhere the location of the water table is mentioned, so that's why we are considering that the water table is at a greater depth. So there is no influence of the water table on the bearing capacity of the given footing. So therefore, this term either we can neglect or we can consider this term as 1. Okay. So therefore, this bearing capacity equation will be modified as Q mu. Okay. A few more things. So for this problem, since the soil, underlying soil is basically clay, so NQ is 1, N gamma is 0. So this value is 0. So third term will be vanished, and this whole term nq minus 1, 1 minus 1. So this will also vanish. Okay, this total term. So therefore, leaving behind only the first term, cu nc sc dc. So now the problem becomes very easy. cu you have calculated as 50 kPa, so we have to just calculate the other values for AC, DC and IC, and NC you know it's 5.14 for phi equals to 0 degree as per IS 6403. Okay, so we'll calculate this AC value, DC value and IC value from this chart, and this is given, this chart is given in basically this IS 6403 code. Okay, so this AC, so it's basically AC, this is 1 plus 0.4 times B by L. This is for, 0.2. This is 0.2 times B by L for a rectangular footing. Now, why I am choosing this rectangular footing? Because the footing is square. The shape of the footing is square. It's a 2 meter by 2 meter. Now, why I am choosing this rectangular footing? The equation for shape factor for rectangular footing. What is the logic behind this selection? The logic is, as I have already mentioned, that to calculate these factors, shape and depth factors, you have to consider the modified width, not the original width, since the load is eccentric about the center of the footing. Now, as you can see, after the modification of the initial area, plan area, the footing is no more square. It becomes a rectangular footing with dimension 0.88 meter by 2 meter. So this dimension is 0.88 meter and the length is 2 meter. So therefore, you have to consider the equation of shape factor corresponding to a rectangular footing, not a square footing. So this is B prime by L. So obviously this will be 1 plus 0.2 times 0.88 divided by 2. So what would be the value? I think it will be 1.088. Now coming to DC, so it will be 1 plus 0.2. Okay, here phi value is less than 10 degree. So please keep in mind the past expression. Oh no, sorry. I am doing one mistake. So this is for DQ part. Okay. So for DC part, for any phi, this is the expression. So 1 plus 0.2 df again d prime tan square. Tan 45 degree plus 5%. Okay, now you know the d prime value, df value, the depth of the foundation. So it's basically 1.5 meter. So it's 1.5 meter, the b prime value 0.88, and this part it will be tan 45, that means 1. So 1 plus 0.2 multiplied by 1.5 divided by 0.88, that means 1.34. And what about IC? So IC would be 1 minus alpha degree by 90 degrees square. So 1 minus alpha degree by 90 degrees square, and here the alpha value is 10.60. Okay, so this is the vertical inclination of the load. So 1 minus 10.60 divided by 90 square, it's 0.78. You can take it as 0.78. and the net ultimate bearing capacity Q NU. So this is Q NC SC. Okay. Now you have to just simply substitute this value. Okay, so this dimension is your 0.8 meter. This is your L and this is your B. Okay. So therefore, this QNU, this will be 50 times 5.14 times AC is 1.088, DC is 1.34 multiplied by 0.70. Okay. Yes. So what would be the final value? Two 92.25 kilonewton. Now to determine the factor of safety against bearing, so against the net ultimate bearing capacity, so to determine the factor of safety, so it will be simply QNU divided by the applied load in the vertical direction. So QNU is nothing but, capital QNU is nothing but small QNU multiplied by the modified area P prime multiplied by L divided by the capital P. Now QNU is 290.92.25, B prime is 0.88, L is 2, and the vertical load is 50 kilonewton. So 6.43. This is the. Now, in this question, so only the factor of safety against bearing is basically asked to determine. Now, what if the factor of safety against the sliding is to determine? Then how we can determine the factor of safety against sliding? So this is factor of safety against bearing. Now, if you need to determine the factor of safety against sliding, then what would be your answer? So it will be V tan delta plus C prime A divided by H. Now, what is delta? Delta is basically the angle of internal friction between the base of the foundation and the soil. So this is soil and this is the base. Okay. So the angle of internal friction between the soil and the base. So it's generally taken as 0.8 times pi. And what is C prime? This is the addition along this base. Okay, and this is taken as 0.7 times cohesion. And A, you know, A means the modified area, 0.88 times 2. Then this H value, I think this value also you know, so you can easily determine the factor of safety. Okay, so this would be for the factor of safety against sliding. Now there is one more question for you. So you are getting, or we are getting, the eccentricity of the given vertical load. Here you can see that the eccentricity of the given load you are getting as 0.56 meter. So this value is 0.56. So is this allowable eccentricity? Is this allowable from practical point of view? should you recommend this eccentricity in the practical scenario? Now, what should be your concern to basically allow for some eccentricity of the resultant load, which is basically acting on the footing? What should be your primary concern? So the primary concern, okay, so I will not take much time. I will discuss uh, a little bit about this concept. So your primary concern should be about the tension crack. Okay. Now, in the first problem, we have discussed about it. So this is the column. This is supported by this footing, and you are basically having some eccentric load. This is eccentric with respect to the center. So therefore, you will not be having only the axial load. In addition to the axial load, you will be having some moment. Why? Because the eccentricity multiplied by the result, this vertical load will give you some moment, okay, about this vertical axis which is passing through the CG of the cross section of center of the footing. Now, if this load is if this footing is subjected to a vertical load as well as a moment, then what will be your distribution? The stress distribution beneath the footing. So it will be something like that. Here it will be sigma max, and here it will be sigma mean. Now sigma max, okay, sigma max. So you need to consider, or you need to check whether this sigma max is basically, it can be resisted by the bearing capacity of the footing. So there is a sufficient margin of the soil bearing capacity against this sigma max. So sigma max, you can take this criteria as bearing capacity criteria. So QNU divided by sigma max, I think it should be greater than 2.5 times to 2.5 to 3. Okay. Now what is about this sigma mean? So sigma mean, you need to be very careful about this sigma mean, that this sigma mean should never be less than 0. It should be always positive. Why? Because there is a chance this sigma mean can be 0. So this is P by A minus my by I. So for some specific circumstances, you can experience a negative value of sigma mean. Now what does it indicate? A negative value of sigma mean. So a negative value of sigma mean indicates that some part of the soil beneath the foundation is in tension. So there is no contact between the adjacent soil and the footing. So this part is basically in tension. And you know that soil is very weak in tension. It can resist the compression, but it cannot resist the tension. So it's very, very weak in tension. And as and when there is a tension generated beneath the footing base, there is a gap basically created between the soil, adjacent soil, and the footing surface or the footing. Okay, so therefore you have to basically very careful about this permissible value of this eccentricity, because this M is basically, this Y is basically coming from the footing geometry. If this is your B, so at the footing edge, this Y can have a maximum value of B by 2. and this I is also governed by the footing geometry, something BD cube by 12. Okay, so if I D, consider this is the D, or for a plan area, if we take this dimension or length as L, so BL cube by 12 or LB cube by 12. About the direction of the footing, means length or width direction. However, this M, this is the product of P times E. This is the vertical load and this is the eccentricity at which this load is acting from the center. So therefore, you can control this E, this eccentricity. So you need to basically control this E to not getting any tension beneath the foundation or the footing base. Okay, now how you can control? So you can control by minimizing this sigma mean to a value of 0. So this is the least desirable condition. Okay, so this sigma mean now if this sigma mean is 0, so this is P time P divided by BL. BL is the capital B times L, this is the area. Okay, so right now I am not talking about the modified area. So B times L, and then this M is P times C, then this is B cube L by 12, and this is B by 2, this is 0. Now if we solve this equation, you will get the value of maximum eccentricity E max as B by 6. Okay, now this is for one way eccentricity. Now similarly, you will get the maximum permissible eccentricity along the length direction as L by 6. Okay, now for a rectangular footing, suppose this is the rectangular footing, the top view or the plan view of the rectangular footing, and this is the CG. So you can allow for an eccentricity of at most B by 6, L by 6 along the length direction and B by 6 along the width direction. So therefore, you will be having a shape of something, you can call it as rhombus. Okay, so your externally applied load should act within this region. If the externally applied load is basically acting within this region, there is no chance of building up of tension at the footing base. Otherwise, you will be having tension at the footing base. And this area is known as Kern. Okay, so this is from the fundamentals of solid mechanics concept. So this is known as Kern. Okay, so this is all about the maximum permissible eccentricity to not getting any tension at the footing base. Okay, so this is the now coming to problem 3. So this is the determination. This is about the determination of safe load carrying capacity of pile using Tomlinson's method. Okay, so we'll first read out the problem statement. So a 20 meter long and 400 mm diameter pile was driven into granular soil strata of friction angle value 37 degree. The water table is at a great depth. The average unit weight of soil is 18.7 kilonewton per meter cube. Calculate the safe load carrying capacity of the pile using Tomlinson's method. Given the bearing capacity factor as 75, this is the earth pressure coefficient, as you know, this is 2, delta 0.75 times pi. Okay, this is the same pi, and the factor of safety 2.5. Consider pile to be weightless and do not consider critical depth concept and take full tip resistance. Okay, so this statement is very critical. Okay, very essential to solve this kind of problem or to solve the right answer. Okay, so this is the problem geometry. This is the pile of diameter 400 mm or 0.4 meter and length 20 meter, L 20 meter length. Granular soil having friction angle 37. Now, as you know that when a pile is basically subjected to, so right now we are basically calculating the safe load carrying capacity of the pile in compression. Okay, so when a pile is basically subjected to some load P, compressive load P, so it will be basically resisted by two components. So one is friction along the periphery of the pile, okay, surface of the pile, skin friction, and another component is point bearing resistance. The resistance you can derive from these two parts, the point bearing resistance and the skin friction resistance. So therefore, this ultimate resistance of the pile you can calculate QU, QPU, this is the ultimate point bearing resistance, and QA friction resistance. Now this friction resistance and the point bearing resistance you can calculate by multiplying the concerning area with the unit resistance in the sense QPU, this is the unit point bearing resistance. If you multiply this unit point bearing resistance with the base area, you will get the ultimate point bearing resistance. And similarly, if you multiply the unit skin friction resistance, sorry, this is denoted as A base, with the surface area of the footing, then you will get the friction or frictional resistance. So if you add these two components, you will be getting the ultimate resistance of the pile. And if you divide this ultimate resistance by the recommended factor of safety, you will be ending up with the safe load carrying capacity of the pile. Now, this AB and AA somehow we know from the pile geometry. So AB, this is nothing but pi by 4 d square. And what is AS? This AS is nothing but pi dl. So this is the surface area of the cylindrical pile, and this is the cross sectional area at the base of the pile. And D you know 0.4 meter, L you know this is 20 meter. So therefore, you only need to know this QPU and FS. Now, how you can calculate this QPU? This QPU, it will be sigma prime multiplied by NQ. Okay. Now, what is sigma prime? Sigma prime is the effective overburden pressure, vertical effective overburden pressure at this level, at the tip level, okay, or at the base level of the pile. And what is Fs? So Fs, this is nothing but K sigma average times. Now, sigma average, this is, as you know, that as you go below from the ground surface, you will be having a greater, or for this problem, at least for this specific problem, you will be having a linear variation in the effective vertical overburden pressure. So therefore, since this effective vertical overburden pressure is varying along the length of the pile, so we have to consider some average of this variation. And if you multiply this with the tan delta, with the K, so you will be getting the horizontal stress. And if you multiply this horizontal stress with the friction value, then you will be getting the frictional resistance. So it's something like this. So this is the N normal stress, and the friction coefficient of this surface is mu. So what would be the frictional resistance? So it will be mu times N. And here N is nothing but this K times sigma AB average. K is the lateral pressure coefficient and sigma B average is the effective vertical pressure, average effective vertical pressure along the length of the pile. And this mu is nothing but tan delta. Delta is nothing but the angle of internal friction between this pile material and the adjacent soil mass. Okay. So this is mentioned as 0.75 times pi. Okay. So now it becomes very easy. Just you have to substitute these values, and before that you have to calculate this distribution of the effective vertical overburden pressure along the length of the pile. Okay. So one more thing. So in this problem, these values NQ, K, delta, these values are directly given to you. If this is not the case, in the examination, then you have to calculate this values. And since we are considering this Tomlinson's method, so this NQ value you have to calculate from this chart. Okay, this Jand-Shap's bearing capacity factor, and this chart is basically given in Murthy, the book written by Murthy. Okay, so you have to calculate this NQ from this chart. Now to calculate this NQ value, first you need to know the angle of internal friction phi and the L by D ratio. So L by D ratio you know, because L is 20 meter and D is 0.4 meter. So you can easily calculate the L by D ratio. You know the angle of internal friction, it's 37 degree for this problem. So therefore you can easily calculate this bearing capacity factor. So if you calculate, I think or I hope this value should match with the value given to this problem. Okay, as 75. Okay, so we can basically give a try. Now, what is the L by D ratio for this problem? So this is 20 by 0.4. So that means 50. And this is 37. So this is 35, this is 40. So something in between this 37.5. And L by D 50. So 5, 20, 70. So in between 20 and 70. So something here. Okay. Okay. Now bearing capacity lies in between 50 and 100. So therefore 150 by 2, that means you can take this value as 70. And as given to this problem. Similarly for earth pressure coefficient and the delta value. So first you have to know what is the type of sand. So whether it is loose sand or dense sand, and what is the type of pile material, whether it's steel, concrete or timber. So depending on these two conditions, you can easily get the values of K and delta. So for this problem, so it's a you can take this pile material as concrete and the granular soil with phi equals to 37 degrees. So it will be dense sand. So you can basically get the relative density from this chart depending on the angle of internal friction. So as the angle of internal friction is 37 degrees, so it's basically dense sand. And the pile material you can take it as concrete. So if the pile material is concrete and the sand is dense, so the K value would be 2 and the delta value would be 0.75 times pi. Okay. So this is the approach to calculate K and values for K and delta. Now we'll substitute the given values to the equation of the ultimate pile load capacity. So Q. So okay. So first let us determine the distribution of effective overburden pressure, vertical effective overburden pressure along the pile length. Now, since there is no water table, so the distribution will be simply look like this. So it will start from some value of 0 at the ground surface and to a value of gamma times L. Now what is the value of gamma? So gamma is given as 18.7 kilonewton per meter cube. Okay, and the pile length is 20. So 18.7 multiplied by 20, it will give you 374 kilonewton per meter square effective vertical stress at the pile tip. Okay, so this is 20 meter. And this is 0. So therefore this sigma average it will be 0 plus 374 by 187 kPa, and it is the effective vertical stress at the pile tip. So therefore this QU it will be NQ times sigma prime. So this is sigma prime times NQ. So QPU. Okay, QPU. So sigma NQ times sigma prime. So 187. 374 multiplied by 75. 374 multiplied by 75, that means 28050 kilonewton per meter square. And if this is 2 times 187 and tan of 0.75 into 37. Okay. Okay, so this is 196.77. Now we'll calculate this surface area and the cross sectional area at the base. So AB, so it's basically pi by 4 into 0.4 square. So this is 0.126 meter square, and the surface area this is pi into 0.4 into 20. So this is 25.13. Okay. Okay, now we have to just simply substitute these values. So for the point bearing resistance, it will be 28050 multiplied by 0.126. 28050 multiplied by 0.126. And for the skin friction resistance, it will be 196.77. 196.77 multiplied by the surface area, that is 25.13. So this will be 0.16 as 8479. I am getting something 8479.13. Okay, so I may be wrong, please correct me for this calculation part. And finally, the safe load carrying capacity. So for determining the safe load carrying capacity, you have to divide this ultimate load carrying capacity with the recommended factor of safety. So here the recommended factor of safety is 2.5. Okay, so 8479.13 divided by 2.5. That means 3391.65 kilonewton, and this is the okay. So in this way, you can calculate the safe load carrying capacity where the pile dimension is given, that is the diameter of the pile and the length of the pile. The soil properties are given, and this bearing capacity factor, the earth pressure coefficient, and the delta value is given. And in addition to that, the recommended factor of safety is also given. Okay, and please keep in mind that for this problem we didn't consider any critical depth concept, and we have taken the full tip resistance. Okay. Okay. Now coming to next problem, that is problem 4. So this is taken from GATE examination 2017. So it's proposed to drive H pile up to a depth of 7 meters at a construction site. The average surface area of the H pile is 3 meters square per meter length. The soil at the site is homogeneous sand having an effective friction angle of 32 degrees. The groundwater table is at a depth of 2 meters below the ground surface, and the unit weights of the soil above and below the water table are 16 kilonewton per meter cube and 19 kilonewton per meter cube respectively. Assume the earth pressure coefficient K equals to 1 and the angle of wall friction delta is 23 degree. Determine the total axial frictional resistance in kilonewton mobilized on the pile against driving. So unlike the previous problem, in this problem we have to report only the axial frictional resistance component. Okay, so we need not to consider, or we need not to calculate the point bearing resistance, and further we need not to apply any factor of safety. So here we have to just report the mobilized axial frictional resistance against driving. Now how we can solve this problem? So we can solve this problem in the similar fashion as we did in the previous problem. So this QS, so we have basically denoted this friction component as QF. Okay, QF, and this QF is nothing but FS into AS. Now this FS you can determine from this expression K sigma V average and okay. Now there is one more difference between the previous problem and in this problem, that is the location of the water table. So earlier in the previous problem there was no water table, at least within the length of the pipe. However, in this problem the water table is basically located at a depth of 2 meters from the ground surface. So therefore this distribution of effective vertical stress will not linearly vary from the ground surface to the base of the pipe. Okay, so it will not be simply a linear variation from the base of from the ground surface to the base of the pipe. So therefore this calculation of effective vertical pressure along the length of the pipe is necessary, and you need to calculate this variation at first. Okay, so now if we calculate this variation, so suppose this is the length starting from 0 meter to 7 meter. So this level is 7 meter, and the water table is basically encountered at a depth of 2 meter. Okay, this is 2 meter. Now this gamma value for soil, above the water table is 16 kilonewton per meter cube, as mentioned in this problem. It's 16 kilonewton per meter cube, and the gamma value for soil below the water table, it's 19 kilonewton per meter cube. Okay, so the effective vertical pressure will start from a value of 0 from the ground surface to 16 multiplied by 2, that is 32 kPa at the water table location. Okay, so this diagram is given in kPa. Now once it encounters the water table, so you have to consider the pore water pressure also. So you have to calculate total stress, you have to calculate pore water pressure, then you have to subtract the pore water pressure from the total stress to calculate the effective stress at that level. Okay, at that level in the sense level, any level below the water table location, or in other words you can directly calculate by the product of submerged unit weight times the concerning depth. Okay, so we'll follow that concept. So gamma sat is 19, so obviously gamma submerged will be 19 minus 10, 9 Newton per meter cube. So this value will start from 32 at the water table location, and it will end with a value of 32, so it will be 32 plus 9 times 7 minus, okay, that means this height below the, or length below the water table. This is groundwater table. So 32 plus 9 multiplied by 5, that means 45. 32 plus 45, that means 77. Yeah, 77 kPa. So therefore, to calculate the frictional resistance, unit frictional or unit skin resistance, you have to consider these two segments separately. So this will be segment 1, and this will be segment 2. Okay. Now for segment 1, the average effective vertical stress sigma prime AB, it will be simply 32 by 2. That means, however, for segment 2, this average vertical stress, it will be average effective vertical stress, it will be 32 plus 77 divided by 2. Okay, 32 plus 77 divided by 2, that means 54.5 kP. Now we have determined the average vertical effective stress for these two segments separately. So therefore, we can calculate the unit skin friction resistance which is applicable for these two segments individually. Okay, so FS1 for segment 1, so it will be K times sigma B, sigma AB average and delta. So K for this problem is given as 1 and delta is given as 23 degree. Okay, so 1 multiplied by 16 multiplied by 10, 23. Okay. Now what is the surface area for this segment? So A is 1. So this is simply, so here the pile dimension is not given, rather the average surface area of the H pile is given as 3 meter square per meter length. So for a length of 2 meter for segment 1, this AS1 would be 3 multiplied by 2, that means 6 meter square, and this is kilonewton per meter square. Okay, so this is for segment 1. Similarly for segment 2, this A phase 2 unit skin friction resistance, it will be 1 multiplied by 54.5 multiplied by 1023 kilonewton per meter square, and AH2 it will be 3 multiplied by 5, okay, or 7 minus 2, the remaining length of the pile, which is 15 per meter square. Therefore the total skin friction resistance mobilized, okay, so this is QF. So this will be FS1 AS1 plus FH2 AH2. So therefore it will be 16 1023 multiplied by 6 plus 54.5 and 23 multiplied by 6. So please calculate and let me know the final answer. 16 into 6 plus 54.5 into 15 into 10. Okay, so it's I think 387.5 357.76 kilonewton, or we can approximate this value as 358. This is the final answer. So in this way, we can calculate the total axial frictional resistance in kilonewton mobilized on the pile against driving. So please keep in mind that in this problem, we didn't consider or we didn't impose any factor of safety, because here this kind of factor of safety is not mentioned, and again we didn't calculate or consider the point bearing resistance, because we have to only report the total axial frictional resistance mobilized on the pile against driving. Okay. So the only difference between the earlier problem and the present problem is that, so in the earlier problem, no water table is basically mentioned, at least within the length of the pile. However, in this problem, we have encountered the groundwater table at a depth of 2 meters from the ground surface. So therefore, for the calculation of the unit skin friction resistance, we need to consider two segments separately, and for each of this individual segment, we have to calculate the unit skin friction resistance and the respective surface area separately. Okay, then we have to add these two components to get the final contribution. Okay, now this is problem 5. So in this problem, we have to match this list 1 with list 2. So in list 1, basically this type of soil is basically mentioned. So A, this is cohesive soil. In B, this is loose granular soil. C, this is dense sand, and D, this is expansive soil. Now in list 2, a few conditions are mentioned like that. So first of all, it's critical depth, which is equated to 20 times of D, where D is the diameter of the pile. Then in option 2, or in the second entity, its underdamped pile is most suitable. Then in entity 3, driven pile is most suitable, and in entity 4, this is the uniform stress distribution. However, highest settlement at center and lowest at corners for a flexible footing. Now you can easily understand that what does it try to mean, that for what type of soil this condition is basically perfectly matching. Okay, so for an example, I am starting with cohesive soil. So it's very obvious that this cohesive soil, this entity 4 is the ideal choice. Why? Because if you observe the stress and settlement distribution beneath the footing, so depending on the type of soil and depending on the rigidity of the footing, so the footing can be rigid or flexible, and the soil can be cohesionless or cohesive. So now, considering the combinations of these 4 conditions, so you will be ending up with 4 distribution as basically shown in this slide. So in the first condition, this is flexible footing on cohesionless soil. This is in the second, it's flexible footing on cohesive soil, and in the third, it's rigid footing on cohesionless soil, and finally, this is rigid footing on cohesive soil. Now, among these 4 conditions, you can easily understand that for the given problem, so this cohesive soil is matching with flexible footing, means for flexible footing resting on cohesive soil, the distribution of stress would be uniform. However, the settlement will be highest at the center and it will be lowest at the corners as mentioned in the problem. Okay, so distribution of stress would be uniform throughout the base of the footing. However, settlement will be highest at the center and lowest at corners when the footing is flexible and it's sitting on a purely cohesive soil. Okay, so this second condition is basically, this condition is basically talking about in this problem. Therefore, A is matching with entity 4. Now coming to this entity B, loose granular soil. Now for loose granular soil, which pile is suitable, most suitable? So you should know, for loose granular soil, this driven pile is most suitable. Why? Because when the pile is basically driven inside the loose granular soil deposit, so what it will do? So it will basically compact the surrounding soil mass. So therefore, the initially loose granular deposit will achieve a compacted configuration due to the construction of this driven pile. Therefore, for loose granular soil, driven pile is most suitable. So B is matching with entity 3. So likewise, for dense sand, you know that the critical depth of a pile is restricted to 20 times of the diameter of the pile. So C is matching with entity 3. So we'll basically come on to the topic that what is known as critical depth. Okay. And lastly, this expansive soil, for expansive soil, this underdamped pile is most suitable. So D matching with entity 4. So therefore, I hope option C is the correct answer. Oh, sorry. This will be 1. This is the right. Yeah. So again, for a flexible footing resting on cohesive soil, the distribution of stress beneath the footing will be uniform. However, settlement will be highest at the center and lowest at the corners, as can be seen from this slide. And secondly, this driven pile is most suitable for loose granular soil, and critical depth of a pile is restricted to 20 times of the diameter of the pile for dense sand, and underdamped pile is most suitable for expansive soil. So considering these conditions, option C is the correct answer. Okay. Okay. So now we'll end this session by taking one homework problem. So this homework problem is taken from this engineering service examination 2023. So where a pre-stressed concrete pile of 0.5 meter diameter is driven in medium dense sand up to 10 meter depth. The groundwater table is at 3 meter depth below the surface, and the properties of the sand are given as angle of internal friction of the sand is 30 degrees, angle of wall friction between pile and sand is 20 degrees, post driving horizontal arc pressure coefficient, that is this K value is given as 1, saturated unit weight of the sand is given as 19 kilonewton per meter cube, and unit weight of sand above groundwater table is given as 17 kilonewton per meter cube. Now, if the unit sap resistance reaches the limiting value at 15 times D, where D is the diameter of the pile, estimate the skin friction resistance of the pile. Now, what does it mean by this statement? If the unit sap resistance reaches a limiting value at 15 times D. So this statement basically talks about the critical depth concept. Now, what is this critical depth concept? So critical depth concept is nothing but, suppose this is the pile length L, and if you try to figure out the unit skin friction resistance along the length of the pile, so for that you first need to calculate the effective vertical effective pressure along the length of the pile. So this is the primary criteria to calculate the unit skin friction resistance mobilized along the length of the pile. Now, in the earlier problem, I think in problem 4, we basically considered problem 4 and again problem 3, we basically considered this distribution, this effective vertical stress distribution from the ground surface to the pile tip as a full magnitude, means the intensity what we are getting from this distribution, we are taking this value directly. However, in the field condition, it's noticed that this distribution of stress is basically reaches a limiting value at some depth. Okay, suppose this depth is D critical or L critical, and then this magnitude remains constant. So you are not basically having the full distribution of this effective vertical stress as you have got in the previous cases, means problems 3 and 4. So as per the critical depth concept, the distribution of effective vertical stress will be limited to a length of L critical, and that will know what is the value of this L critical, and thereafter this distribution will be having a constant value. There should not be any variation. That means this is the limiting case. So we are having the limiting value at the critical length or critical depth, and thereafter this limiting value remains constant. Okay, and as per the literature, this this critical depth is given as 15 times D if the sand is medium dense, and it's 20 times D if the sand is dense. Okay, so as we have seen from this problem, for dense sand the critical depth is 20 times D, where D is the diameter of the pile. And for this problem, homework problem, since we are dealing with this medium dense sand, so here the critical depth is mentioned as 15 times D. So the meaning of this statement is that the critical depth of the given pile is given as 15 times diameter of the pile. So you have to only consider the vertical effective stress distribution up to the length of fully up to the length of 15 times D. Then whatever magnitude you will be getting at this level of 15 times D, this magnitude will remain constant throughout the remaining length of the pile. So it will not increase or it will not vary for the remaining height of length of the pile. Okay, so therefore, considering this critical length concept, first we'll try to establish the variation of the effective stress along the length of the pile. So if this is the length of the pile, the length of the pile is given as 10 meter for this problem. So this is 0 meter elevation view, and this is 10 meter. Okay, now this problem tells about that the critical length is 15 times D, and here the D value is 0.5 meter. So therefore the critical length is 7.5 meter. So if we mark 7.5 meter, it will be here. Okay, now one more condition is talked about in this problem, that is the location of the groundwater table. So location of the groundwater table is basically at a depth of 3 meter. So this is the location, suppose 3 meter. And what are the densities of the soil above and below the groundwater? So above it is 17 kilonewton per meter cube, and below the saturated unit weight is 19 kilonewton per meter cube. So if this is the location of groundwater table, so above this is 17 kilonewton per meter cube, and below this is 19 kilonewton per meter cube. So this is gamma sat. So obviously, if we consider the unit weight of water as 10, the submerged unit weight would be 9 kilonewton per meter cube. So Now we'll try to establish the effective vertical stress distribution along the whole length of the pile. So this distribution again would be in kPa. So therefore, starting from ground surface to the location of groundwater table, this value would be 17 times 3. That means 51 kPa. Okay. And then from 3 meter, that is the groundwater table location to the critical, up to the critical length. So it will be this value would be 51. Sorry. So this is 17 multiplied by 3, that means 51, and here this is 51 plus 9 multiplied by 7.5 minus 3. So this is the length in between groundwater table and the critical length, that means 4.5. Okay, so this value would be 51 plus 9 into 4.5. So 91.5. Now this 91.5 value will remain constant throughout the remaining length of the pile. So it will not increase anymore. Okay. This is the variation as per critical length concept. So if we don't consider the critical length concept, so this 91.5 will go on increasing, or go on increasing as we basically vary, as we basically move down the deposit. So if we basically go inside the deposit to a deeper depth, we will be having a greater effective vertical pressure. However, as per the critical length concept, we have to limit this distribution to this constant value of intensity or magnitude 91. Now, similar to the previous problem, we divided the entire pile length into two segments. So the first segment in between ground surface and the water table location, and the next segment in between groundwater table and the base of the pile. However, in this problem, and as per the problem geometry, we have to divide the entire pile length into 3 segments. Okay, so this is segment 1, and it will be in between 0 to 3 meter, that is ground surface to the water table location. Then segment 2, it will be in between 3 meter to 7.5 meter, that is groundwater table to the up to the critical length. And finally segment 3, that is the remaining length of the pile. Okay, so critical length to the base of the pile, so 7.5 to 10 meter. Okay, so now the job remains same, that you have to first calculate the unit skin resistance, unit skin friction resistance for each of this individual segment. Then you have to calculate the surface area for each of this individual segment, and then you have to multiply the surface area with the unit skin friction resistance to get the total skin friction resistance. And if you add the contribution considering all the segments, you will be having the final ultimate skin friction resistance that you have to report for this problem. Okay, so I will try to complete this problem as soon as possible. So this segment 1, okay, so segment 1, and sorry, and this is segment 2, and this is segment. So for segment 1, so the average vertical stress, first you need to know what is the average effective vertical stress for segment 1. Sigma AB prime, this is 51 by 2. Okay, so this is in kPa. This is for segment 1. Then segment 2, this is 51 plus 91.5 by 2, and for segment 3, this is simply 91.5 kPa. So for segment 1, then therefore this average effective vertical stress would be 25.5. Here this would be 71.2. Okay. Okay. So now the earth pressure coefficient, the post driving horizontal earth pressure coefficient is given as 1, and the angle of wall friction between pile and sand is given as 20 degrees. So therefore, the unit skin friction resistance F is 1. This will be 1 multiplied by 25.5 multiplied by 10 of 20. Okay. So this is Kp. And what is the surface area? The surface area A is 1. So this will be pi dh. The d value is 0.5 meter. Diameter of the pile is given as 0.5 meter. Now what is h or L in this zone, in this segment? The L is in this region 3 minus 0. That means 3 meter. Okay. Okay. Now coming to segment 2, Fh2 you can calculate in a similar fashion. So 1 multiplied by 71.25 into 1020 kPa, and Ah2 5 times 0.5 into 7 minus 7.5 minus 2. Okay, this much meter square. And if S3, this would be 1 times 91.5 tan of 20, and AS3 10 minus 7.5. So the total frictional resistance, skin friction resistance, would be Fs1, As1, Fh2, Ah2 plus Fs3, As3. Now I hope if you calculate this value, you should get the final answer as 357. Okay, kilometer. So please check. So this part I am leaving up to you. So please check this final answer whether you are getting the same answer or not. So this is the answer. So to get the answer, required answer, just you have to multiply this Fs1 with As1, Fh2 with As2, and S3 with As3. Then you have to add these three components to get the final conclusion. So in this way, you can calculate the skin friction resistance of the given pile of diameter 0.5 meter and length 10 meter, where the depth of groundwater table is at 3 meter below the top surface of the pile of the ground surface. Okay. Okay, and Unlike the previous two problems, in this problem, we have considered the concept of critical length. So, while incorporating the critical length concept, you have to be very careful about the variation of the effective vertical stress, that up to the critical length you will be getting the effective vertical stress distribution as per the usual fashion. However, while you will go beyond the critical length, you will not be having any variation in the effective vertical stress. So whatever magnitude or intensity you will be getting at the level of critical length, so that value will or should remain constant throughout the remaining length of the pipe. Okay, so this is as per critical length concept. So therefore it's very essential whether in the problem statement it's mentioned or not that you have to consider the critical length or not. So as per that condition, the final answer will vary, will change. So it will not remain same if you consider critical length or if you don't consider the critical length concept. Okay. So I think this is for today's session. So in this session, we have mostly tried to utilize or to comprehend the concept of how to calculate the bearing capacity of a footing which is subjected to both eccentric and the inclined loading. And with respect to that eccentric inclined loading, we have determined the factor of safety against bearing, though we can also determine the factor of safety against sliding. Okay, in addition to that, we have learned a little bit about the permissible limit of the eccentricity which you can allow in the practical field condition. So if you basically go beyond, or if you allow the eccentricity beyond the permissible value, then there is a chance of generation of negative pressure at the base of the foundation. Now, once you encounter some negative pressure along the base of the foundation, and you know what will be its consequences. So since the soil is very, very weak in tension, so there will be a separation. So the soil, adjacent soil mass will be separated from the base of the foundation. So therefore, you have to be very careful about this aspect, that in any situation there should not be the chance of generation of negative pressure, or you can say the generation of tension crack beneath the footing base. Okay. Okay. Prior to that, we have seen how to proportion the length of a combined trapezoidal footing when this footing is basically subjected to two column loads of magnitude something I think 2000 kilonewton or 1500 kilonewton. Now, the condition based on which we have proportioned the length of the footing is that the distribution of stress beneath the footing should be or must be uniform. Okay, and for that we have basically implemented the condition that to have a uniformly distributed stress beneath the footing base, we have to pass the resultant load to the centroid of the footing. Otherwise, there is a chance or scope of generation of this externally applied moment, and that will be the product of the axial load with the eccentricity at which the load is basically acting from the center of the footing. Okay. Now coming to the third problem, we have utilized the Tomlinson's method to determine the safe load carrying capacity of a pile. Now the dimension or geometry of the pile is given, the soil properties were given, then the bearing capacity factor, the earth pressure coefficient, the angle of wall friction, all are given, and the recommended factor of safety is also given. Just we have to report the safe load carrying capacity using Tomlinson's method. So we have also discussed if these factors like earth pressure coefficient, bearing capacity factor, and the delta value are not given directly, are not given to us, then we can also determine these parameters through some tables which are given in the literature. But for that, we have to only know what is the criteria or what is the parameters first we have to determine. Suppose for determining the bearing capacity factor NQ, we need to know what is the angle of internal friction and what is the L by D ratio of the pipe. So if you know these two parameters, then you can easily determine the NQ value from the chart given in the literature. Okay. Now coming to the fifth problem. So we have basically dealt with H pile, and this pile is basically driven up to a depth of I of 7 meter. So for that pile, we have determined the total axial skin friction resistance mobilized along the length of the pile without any consideration to factor of safety. Okay, and since this is skin friction resistance, so there is no chance or scope to deter, or there is no requirement for calculating the point bearing resistance. Okay, now in problem 5, two tables or two tables are given to us. So first of all, in table 1, a few soil types are given, and in table 2 some conditions are given. So we have to match the entities of table 1 with entities of table 2, okay, appropriately. And in the homework problem, so it's no more a homework problem, so we have solved this homework problem already. So in this problem, we have to report the again the skin friction resistance of a pre-stressed concrete pile of diameter 0.5 meter and depth length 10 meter. Okay, now the fundamental difference between this homework problem and the earlier problems is that, so in the earlier problem we didn't consider the critical depth concept or critical length concept, but in this problem we have basically implemented this concept, and according to this concept we have reported the skin friction resistance. Okay, so a small part I have left on you, so please try this part at your home and let me know whether if you encounter any problems or if you face any difficulties in the next session. So for your information, we'll again meet on 10th September, that is coming Sunday at 5. So thanks a lot for joining this session. Now wait for a few minutes. So if you have any more confusion or doubts, you can ask. Okay.